All right, we're going to keep going with our study in Unit 14. We're going to talk about something called the correlation coefficient. So the I can statement for 14.2 is I can use lines of best fit and the correlation coefficient. So we'll talk about what the correlation coefficient is in just a second. We've got a warm-up right here. It says the correlations for the scatter plots below go from negative to positive. On a scale of negative 100 to positive 100, rate how well you feel a line would fit the data. Negative 100 is perfect for a negative slope, so that's going to be this one right here. So I'm going to go ahead and put a negative 100 on that one. And positive 100 is perfect for a positive slope. So this is a perfect positive line right here. So we're going to put positive 100 on that one. Okay. Now, right in the middle of the two of those is just a big blob of numbers on the scatter plot. So we're going to put 0 because that would be right in the middle. Now, this isn't a perfect science. There's nothing absolute about this. What we're going to do is we're going to say, hey, this is a line that goes down that would roughly fit this, and this would roughly fit a line that has a negative slope. So these are both going to be negative for sure. The question is, how well would a line fit these? Now, we don't have to actually draw a line, but I can imagine a line going through the middle of this one. I would say it's okay, but it's not great, so maybe negative 50 on this one. And this one is even more of a blob, kind of like this one is. So I would say maybe negative 20 or negative 25 or something like that. Again, nothing perfect about that. But if we've got these two rated like this, then we'd probably rate this one as a positive 25 and this one as a positive 50. Okay? Again, nothing perfect about that, nothing scientific there. We're just kind of roughly approximating how well we feel a line would fit that data. Now, when we use this linear regression tool that we used on the calculator last time, this number 4, lin reg, so linear regression, ax plus b, and again, the calculator doesn't use y equals mx plus b, it says ax plus b. So we just kind of need to get used to that. That's what's called a linear regression, and the word regression means returning to a former state. So here's what normally happens. We normally have an equation, and then we make points and a graph from that equation. So we start with the equation, then we make some points, and we come up with the graph and stuff like that. Well, when we do a linear regression, what we're doing is we're turning to a former state. We're kind of doing the opposite here. So we have the points, and then we go back and we make our best guess as to what the equation, so let's write the word equation right here, what equation produced those points. Now, this is very seldom a perfect process. It's very seldom a perfect equation because the points are very seldom in a perfect line. So it's really important to understand how linear regression works and how we can use it to understand and answer some important questions. So I'm going to slide down here so we can take a look at this example. It says the table gives data comparing the number of oil changes each year to the cost of car repairs each year. So this is the number of oil changes listed right here in that top column, and then the bottom column lists the repair costs in dollars for each one of those situations of oil changes. So for the example, this one right here, this one had 6 oil changes, and then the costs were $250 for repairs. And this one is no oil changes, cost $700 in repairs. And this one right here is 10 oil changes, and they didn't have any repair costs. Okay, so this is like L1, or we're going to call this the X list, and this is the Y list. I'll go ahead and put L1 here, and I'll put L2 here. So part A on here says find the equation for the line of best fit, which we know how to do already. So it says, remember, clear the old lists. Do not delete them or you'll have to reset your calculator. Well, it's kind of a good idea to reset our calculator to begin with. So here's what I'm going to do. I'm going to go ahead and pull up the calculator. I'm going to hit second and mem, so second memory. On this one I hit number 7 to reset. I'm going to reset all of the RAM, and number 2 here says, yeah, I'm sure I want to reset. So I'm going to clear this off. And again, we're going to put this data in here. So I'm going to hit stat, and we're going to edit, and we're going to put this in as L1 here and L2 here. So L1 is going to go right here. Notice because I reset it, I've got those totally blank and ready to go. So I'm going to go ahead and put this data in. So I'm going to do 6 and 5. I'm going to go ahead and fill that out. You do the same. Okay, I've got all the data in here. It would be important to note we've got 10 data points over here, so n would equal 10 on this one. And if I come down here as I'm double checking, I go through and check and make sure that I've got, 1, 750. Go through and check every one of these. There's my 10, 0. And then the last one is 7 and 150. We've got that right. So this is empty below here, so we know we're on the 10th one, and we've double checked. We know we've got the data in there. Okay, so what we want to do here is it says come up with that line of best fit, that linear regression equation, and it says round slope and y-intercept to 2 decimal places. So we're going to come back here on the calculator, and I'm going to hit second quit. And remember, to do a linear regression, we're going to hit stat, and then we're going to calculate. So we're going to come over here to calculate, and we're going to hit number 4. Now, if you've got an 83 calculator, the steps are the same to get there, but your window is going to look a little bit different. So I'm going to hit number 4, and it brings this up. Now, if you have an 83, it'll just say linear regression, and then you just hit enter, and it gives you the answer. By default, they always use L1 and L2 for the X list and the Y list. We don't need to worry about any of these other things right now. We're going to come down here, and we're going to hit calculate. So we hit calculate, and this is what it says. So remember, this is y equals mx plus b. So the slope in this case is negative 76.972. So that's not enough to bump that up, so we're going to keep that 0.97. And the y-intercept, the b here, is 715.194. Again, not enough to bump that up. So here's what we're going to write down. We're going to write down for the equation, so right over here, and I'm going to shrink this down just a little bit so I can see it at the same time, make sure I don't make any mistakes. So we get y equals, this would be negative 76.97. We'll put an x on there, okay, and then plus 715.19. Okay, and it says draw the line on the scatter plot, and don't forget to finish the scales and labels. So a couple quick things about this. We'll put the line in Y1 here in just a second, but let's take a look at this. So this is the number of oil changes, and they've labeled this, but they haven't scaled it. So let's check and see. This one right here would be that one 10, 0, because it's right on the y-axis, or sorry, on the x-axis right here. So this is 10, so we go 1, 2, 3, 4. Yeah, each one of those is by 1. So we're going to put a 2 and a 4 and a 6 and an 8 and a 10. That matches up there. And that kind of indicates what our scale is going to be. We're going to start at -1 and go to 11, and we're going to do tick marks every 1. This is scaled, but it's not labeled. So this is repair costs. Repair costs, and I'm not very good at writing vertically, so I'm just going to do that a little bit diagonal. Okay, so repair costs right there. So we've got that scaled and labeled. Now we want to put this in the calculator. So we're going to go to y equals, and I'm going to put in negative 76.97. Okay, got that right. And then we put the x, and then we're going to add the 715, so 715.19. Okay, double check and make sure we've got everything in there. That looks pretty good. Now we're going to set up the window. The window is going to go from -1 to 11. Make it look just like that. And then this x scale is going to be 1, tick mark every 1. And then we're going to go from, well, gosh, if this is 200, that's 100. So this would be -100 all the way up to 800. So -100 up to 800. And then we're going to put a tick mark every 100 units in the y direction. Now what we haven't done yet is we haven't set this up to do the scatter plot. So let's hit second and stat plot. It's off right now, so we're going to hit number 1. We're going to turn it on, so we'll toggle that to on. This is pretty easy because by default it's the scatter plot. Here's the X list L1, the Y list L2, and by default it's that mark right there. So let's hit graph and see what we end up with here. Okay, well the scatter plot looks just like this one, and then we've got this line. Looks like it crosses maybe just above that one, and then maybe about right here. Okay, so I'm going to go ahead and go full size on this one, so I can draw that line and make that look as nice as I possibly can. So it's going to look something like that. Now again, not perfect. So we've got that drawn on there. We've got it scaled and labeled and everything. And it says on a scale of -100 to +100, how well do you feel this line fits the data? Well, first thing we notice is it's going down from left to right. So I'm going to use a negative on this. And then it looks like it fits pretty well. I mean, it doesn't actually hit any of the data points, so it's certainly not perfect. We've got a lot of points below, a couple points above, and stuff like that. So I'm going to say maybe like negative 80 or something. I mean, it seems pretty good. Again, that's totally subjective. You can adjust that if you want to, a little bit up or a little bit down if you want. I mean, you could even go -50 if you want. I mean, maybe you think it's not a very good fit. Now, it says, what are the independent and dependent variables in this situation? So explain that. So if you think about what's going on here, Y is normally the dependent variable because it depends on whatever X is. We pick the X to plug in and then it figures out what the Y is. And that should make sense in this situation because the number of oil changes we do kind of indicates how well we take care of our cars. So if we do lots of oil changes and we're taking really good care of it, our repair costs are going to go down. Okay, so the independent variable in this case, so independent is oil changes. Independent is oil changes, and dependent would be repair costs. Repair costs. Okay. Now, if we want to explain that, we'd say something like this: repair costs depend on oil changes. And I'm going to put in parentheses, take good care. Okay, so if we take good care of our car, our repair costs are going to go down. And it says, describe what the slope and y-intercept mean in the context of this situation. Well, the slope in this case is negative 76.97. And the y-intercept in this case is 715.19. Now remember, the y-intercept, that's going to be dollars. Okay, so that's $715.19. And the slope came from a calculation. Now the slope calculation is always the y's over the x's. So remember, it's the y2 minus y1 over x2 minus x1. So the y's would be dollars. So I'm going to put dollars on the top, and on the bottom would be x's. Those would be oil changes. So oil changes. Okay? And what I'm going to do is I'm going to put a 1 down there, so that's a fraction. So here's what the slope means. The repair costs are going to go down. See how this is negative? They're going to go down $76.97 for every oil change. Okay, so I'm going to write down each oil change saves $76. So $76.97 in repairs. Okay, so there's our interpretation right there of slope. And then for the y-intercept would be, well, that's this right here. It would be the point 0, comma, $715.19. So no oil changes. So no oil changes means, and I'm going to put approximately $715.19 in repairs. Okay, so if we don't do any oil changes, it's going to cost us a lot of money, whereas if we do lots of oil changes and take really good care of our car, then our repair costs are going to go down. And then it says, use the equation to predict repair costs if a car has four oil changes per year. So I'm going to slide this down here. So this linear regression equation, we're going to use this to make a prediction. So the equation would be y equals, now repair costs, if it has 4 oil changes per year, what that means is x is equal to 4. So we've got 4 oil changes. We're looking for something about right here. So maybe a little bit more than $400 in repairs. So I'm going to do negative 76.97 times 4 oil changes. We're going to save $76 roughly for every single one of those oil changes, plus kind of our starting repair costs if we don't do any, $715.19, so $715.19. So I'm going to pull up the calculator and let's see what that gives us here. So I'm going to hit second quit. I'm going to do, let's see, this was negative 76, so negative 76.97 times 4. And then we're going to add the y-intercept, so that's 715.19. Make sure I got everything in there the right way, so I'm going to hit enter. Yeah, I get 407.31, so I'm going to do $407.31. So we would predict that if we do 4 oil changes, it's going to cost us $407.31 in repairs, which remember we said that would be a little bit more than 400. Looks like it's pretty good. Okay, and again, important to note, this is just a prediction. Okay, it's not a perfect estimate. There's always some variation, as you can even see how the points vary above and below the line. Now, I do want to point out one more quick thing that might come in handy once in a while. So your calculator actually stores variables in there. So those are under vars. So I'm going to hit vars, and then I'm going to do y vars. Okay, y-vars are the function and the parametrics and stuff like that. The only one that we're familiar with right now is function. That word should ring a bell. So watch what happens when I hit function. It gives me the list of all of those y equals, all those functions in the y equals menu. So I'm going to hit number 1 because remember that's where we stored this. In fact, I can go back and check this. Yep, y1 is that exact same equation. So what I can do here is I can do vars and y-vars to pull up the name of the function, and then I just do function notation. What we want to do is we want to plug in a 4. So this is literally saying I want to find y1 of 4. So go plug 4 into y1 and tell me what the answer is. So if I hit enter, notice it gives me 407.31. So we're in good shape there. We've got that one right. Okay, so this is great. We'll come back over here, and I'm going to slide down to the bottom of this page, and let's take a look at this. It says, remember, we said there were 2 parts of linear correlation. So there's the strength and the direction. Now, so far, we've just talked about the direction. Does it go up or down? Now we're ready to talk about the correlation coefficient. So write the word coefficient. That's really what we're introducing here. And it tells us something about both the strength and the direction of the relationship. So it talks about both of these. So we're going to be able to quantify the strength and the direction. Now our calculator is going to give us the correlation coefficient, and all we have to do is know what buttons to click, but we do have to make sure that something called the diagnostics are turned on. Now, to turn the diagnostics on, it does depend on the operating system, what calculator you have, but this syntax is going to work and this method is going to work regardless of which TI calculator you have. So the first thing we're going to do is we're going to pull up the catalog. So I'm going to shrink this down here. I'm going to clear off the home screen. Now catalog is above the 0, so I'm going to hit second and 0 for catalog. So second and 0. And this is a catalog of every single operation and function that the calculator does, and it starts off with the A's. Now we could down arrow to get to the D's, or we can realize that most of these buttons have a letter above them, and I want to find the D. So see the green guys right here? The D is right here. So it's above the x to the -1 key. So we're going to hit alpha, that's the green one. So hit the green one, and then we hit x to the -1. Okay, let me just double check here. Well, let's see, there we go. Okay, there we go. Okay, and I think by default it's already in that mode. Let me just go back and double check here. So again, we hit second and 0. Notice the A's up in the corner. If your calculator doesn't do the alpha up in the corner right here, then you do have to hit the alpha and then the x to the -1 key. So I'm just going to go ahead and hit that. It takes me down to the D's, so it just jumps down there really quickly. And we want to find, there's diagnostics off, we want to do diagnostics on. So we're going to go ahead and hit enter. And done. We're all set to go. Okay. So let's see. Here's what happens. We're going to do a linear regression again. So I'm going to hit second quit. Second quit. There we go. Clear everything off. And let's see. So I'm going to hit stat, calculate. I'm going to do a linear regression. So we're going to go down to number 4. We're all set to go there. So I'm going to slide down and hit calculate. So we're going to hit calculate. And there we go. Now, you'll notice that there are 2 other numbers that show up right here. One is r squared and the other one is r. We want the one that says r. We don't want to worry about the r squared. You might learn about that in another class. That is useful, okay, but not for our purposes right now. So this is negative 0.964. We're going to round to 2 decimal places, so this is going to be negative 0.96. So I'm going to write negative 0.96 right there. Now, this is the correlation coefficient. So that second number right here, r, and sometimes we'll refer to that as an r value. This is the correlation coefficient. So the sign of that represents the direction of the relationship, which we already knew. When we were looking at this before, you could tell that this had a negative correlation. Okay, we even wrote that down up here. And this number, the size of that number determines the strength. Okay, so it says right here, it says compare the R value with the answer you gave in part B above. Were you close? Well, what we did when we were kind of doing this rating from -100 to 100 is we can actually put a decimal on here now, because these are always numbers between -1 and +1. So these R values, the smallest it would ever get would be -1, and the biggest it would ever get would be +1. This whole negative 100 to 100 is just kind of a way of getting rid of the decimal. So we maybe rated this at negative 0.8, and it came up to be exactly negative 0.96, or roughly negative 0.96. Okay, so we were pretty close. So let's write down pretty close. Okay, not too bad at all. All right, now we've got the diagnostics on, so we can go ahead and do any other linear correlation problem, and it will automatically calculate the slope, the y-intercept. Again, we're not going to worry about r squared for right now. And then r, the correlation coefficient, it'll have a sign on it, and it'll be a number between -1 and +1. Now, if you need to, you can watch this little video that shows a quicker technique for newer calculators on how to turn on the diagnostics. So let's go ahead and take a look at the next page. Okay, on the second page, we've got another scatter plot done for us. It's not labeled and scaled completely, so we're going to have to fix that in a second. But we've got the age of a car listed right here, and then we've got repair costs listed second. So let's go ahead and put this data in the calculator. It says find the equation for the line of best fit and the correlation coefficient, and then graph the line over the scatter plot. So let's go ahead and get the data in there. I'll pull up the calculator. I'm going to hit second quit. I'm going to go to Stat, I'm going to Edit, and again, I'm going to clear this off. Whoops, I'm going to clear and hit Enter. Come up here, clear, then Enter. That gets rid of those. So go ahead and put in the data, and I'll do the same. Okay, so I've got all the data in here, and I can't stress enough how important it is that you make sure that you type the right stuff in. So it's always a good idea to double check. I counted through here, there are actually 11 data points, and if you go through and check every single one of these, again, it takes some time to put this in and double check and make sure you've got it in there the right way, but yeah. So we've got 11 data points. If you go back through here, check every single one of them, make sure they're right. I know I've got this in here the right way, so I'm in good shape. So we're going to go ahead and find the line of best fit and the correlation coefficient. So here's the cool thing about this. We're going to hit second quit. We're going to go to the home screen. Once we've got that data in, we can make a scatter plot. We can come up with the linear equation, correlation coefficient, all that sort of stuff. Going to be pretty easy. So here's what we do. We're going to hit Stat, and we're going to calculate. We're going to hit number 4. Again, if it's an 83, it'll look a little bit different. We're going to come down here, and we're just going to do Calculate. Notice that we've got the diagnostics on, so now we're seeing y equals ax plus b. We know the slope is 78.57. Again, that we're not going to round that up, okay? And b is 28.57. Same thing, we're not going to round that up. We don't worry about the r squared. That's actually called the coefficient of determination. That's something very different. But we want this right here. We want the correlation coefficient. So I'm going to shrink this down so I can write down that equation there. So the equation is going to be, so we're going to write y equals, this is 78.57x, and then plus 28.57. And the correlation coefficient, I'm going to write down r equals 0.64, and we wouldn't round that up. So we've got the regression equation, we've got our linear equation, and then we've got the correlation coefficient. So I'm going to go ahead and graph this on here. So we're going to go to y equals, I'm going to clear that off, that's the old one, and we're going to put in 78.57, and then an x, and then plus 28.57. So make sure we've got that in there the right way. Looks pretty good. Okay, so we're all set there. Now, the cool thing about this is if we look at this window right here, we go from -1 to, that would be 11, so we're in good shape there. And let's see, if we go 2, 4, 6, 8. So this is the same setup right here. So this is going to be 200, so we're going to go ahead and scale this. 400, 600, 800, so we're in good shape there. But don't forget this, we've got to label that. This is the age of the car. So age of car, okay? So as the age of the car goes up, we have some higher repair costs, and that's kind of indicated in what we're looking at here. You can tell that this is a positive correlation coefficient, so we're going to have a line that goes up from right to left. It matches up. So the slope and the correlation coefficient, they're always going to be the same sign. If this is positive, that's going to be positive. If this is positive, that's going to be positive. And we saw that on the other side where they were negative. Okay, now if we want to double check our stat plot, that is on. We're using L1 and L2, and you can see right here that it is a scatter plot, so we should be in good shape there. I'm going to go ahead and hit graph, and that looks pretty good. Now, you'll notice that it's just barely above the origin right here, and then it goes through roughly that point right there. So I'm going to come over here, and I'm going to say our line goes from here to here, okay? So that looks pretty good. Now, I'm going to come back over on this one. I'm going to make this full size here. And it says, use the equation to predict repair costs if the car is 7 years old. So 7 years old, that's going to be the age of the car. That's going to be x equals 7 right there. And let's see, so we'd have y equals, this is going to be 78.57 times 7, and then plus the 28.57. So let's see what we get here. Let's throw that in the calculator. So I'm going to hit second quit, and I'm going to do 78.57 times 7 years, and then we're going to add $28.57. Now, it didn't ask us to do this, but it might be a good idea to think about this. This is the slope, and what that means is that's $78.57 per, remember this is the Y on the top, so that's the repair cost, that's dollars, and this is per year of age, if we want to think of it that way. And then this right here, if we had no age, so if it were brand new, it's going to cost us $28.57. Okay, and that may come up again in just a second. So I'm going to go ahead and hit enter. So I'm going to go ahead and shrink the screen here so we can see both of these at the same time. And I'm going to fill this in. So this is, what have we got here? $578.56. Now, does this seem reasonable? Does it match up with the pattern that we see here? So if it's 7 years old would be right here, and $578, so on the line it would be right there. So yeah, that fits with the pattern, and it's definitely on the line. So yeah, that seems reasonable. Okay, fairly old car. It's going to cost us quite a bit. Use the repair cost to predict predict repair costs for a brand new car. So remember, a brand new car would be x equals 0. And if you think about it, we were just talking about this. Well, if we do a brand new car, this would be 0. So we wouldn't have any repair costs for each year because it's brand new. It's only going to cost us $28.57. So we're going to put, and again, I could throw this in the calculator. I can actually hit second enter to recall that, and I can put 0 years right here. It's going to give me $28.57. So $28.57. Now, does that seem reasonable? Well, it certainly fits with the pattern, and it shows on this line where it crosses the y-axis just barely above the x-axis, just barely above the origin. Seems pretty reasonable. I mean, we'd hope it doesn't cost us anything for repairs if we've got a brand new car. But again, this isn't a perfect prediction. It's just using this data to come up with a line that says, hey, this is a line of best fit. You can use that to make some predictions. So it says, estimate the age of a car that had $200 in repairs. So this, if you think about it, this is exactly backwards. Okay, what this is saying is, we know how much we have in repairs. Could we make a prediction? Well, this is the repair costs, so that's y. So they're telling us that y equals 200. You tell us the age of the car. You tell us what x is. So we don't know what x is. So here's what we're going to do. We're going to put 200 right here. So 200 equals 78.57x plus 28.57. And then we're going to solve that. So we're going to subtract the 28.57. So let's see what we get here. So we get 200 minus 28.57. We're going to get an answer, so that's 171.43. So 171.43 equals 78.57x. So we're going to divide both sides by 78.57. So let's see what we end up with here. So we'll divide this by 78.57, hit enter, and we get 2.18. So this would be 2.18 years. Remember, X represents the age of the car, so it's going to be 2.18 years old. Now we should kind of look at this and see if this seems reasonable. So if we have $200 in repairs, let's follow this over right here. That would hit the line about right there. And then we'd follow this down. So yeah, that looks reasonable. We could also do this on the calculator. So if I hit graph and I hit trace, it's going to hop on one of those points right there. I can actually hop on the line by doing this. And you'll notice that I can go back and forth on this line. And if I go to about right there, I've got about $200 in repairs, and it says this is 2.19. So I think we did a pretty good job. Looks pretty awesome. So I'm going to come back over here, and let's finish this off by talking about how would you summarize the relationship between the age of the car and the yearly repair costs. And it says be sure to include how the correlation coefficient and line of best fit support your answer. So I'm going to shrink down just a little bit so we can see what this relationship was. And we kind of talked about this already. So the older the car gets, the higher it is in age. Okay, as the years go by, it's going to cost us more in repairs. So we'll say something like this: the older the car, the more the repair costs. Okay. There's a positive correlation for that. So they both do the same thing. When we've got a positive correlation, as the x variable goes up, as this independent variable goes up, as it gets bigger, the y is going to do exactly the same thing. Now remember, if it's a negative correlation, it has an opposite relationship. The bigger x gets, the smaller y gets. Okay, so the correlation coefficient is positive, so I'm going to say R equals positive 0.64. Okay, that means they're both going to do the same thing. They're going to go up and down together. So I think we're in good shape there. And also, this is a pretty good fit. And it says for the next one, it says predict repair costs for a car that is 29 years old. So if a car is 29 years old, so let's see, that means that X is 29. So I'm going to come back over here. I'm going to hit second quit. Now we could just plug into this equation right here, but I'm going to use that vars tool again. I'm going to hit vars and y vars. So remember, we've got this stored in y1 already. So once I bring that up here, I can just plug in 20. So we said 29 years old. So if a car is 29 years old, we get $2,307. And remember, that 0.1 would be 10 cents here. So this is going to be 2307.10. So 2307.10. Okay, and that's dollars. Now, would we have any concerns about this? Well, one concern you probably should have is that is a really old car, and that's a lot of money. And we don't have any data that's anywhere close to that. I mean, I think the oldest car we have is 8 years old. Maybe we had one that was 10 years old. I can't remember if that fit on the graph there. Okay, but yeah, we probably ought to have some concerns. So I'm going to put on here, and I'm going to make this go a little bit bigger here. Okay, so I'm going to say yes. Okay, we don't really have lots of data for cars that old. Okay, not any data for cars that old. Now, this brings up this next point right here. Mathematical models, they're usually only good within what we call the scope of the data that's used to produce them. So the data that we had on this one, we didn't have a whole bunch of data. We had data for cars that were anywhere from, the earliest was 3 years old and the latest was 8 years old. So we really didn't have a lot of data for that. So what we want to say in this case is we want to say, we want to be very careful when making data for predictions that is outside. So let's say the word outside right here, outside the scope of our model. So when we had 29 years old, that was way outside the scope of our model. We kind of want to stick to things that are in maybe that 0 to 10 year time frame. And we should recognize that predictions are not perfect. They are just our best guess. Given the data that we've got in this situation. Now, if we get more data or we get better data, then we can adjust our model and we'll be able to make better predictions or better estimates. Now, the last thing we want to go over is I want to come back to what we started with in the warm-up. These are some examples of scatter plots and what their rough correlations would be if you actually went through and calculated these with a computer or a calculator. So these are the R values. So this is a perfect line that has a negative slope. So we'd say that's perfect on this end for a negative correlation, and this is perfect on the positive end for a correlation. Now in between, if there's no correlation at all, we'd say that's 0. And then this is kind of a continuum. We go from perfect to strong to moderate to weak to no correlation on the negative direction. And then we have a weak positive correlation, a moderate positive correlation, a strong positive correlation, and then a perfect positive correlation. So this is roughly what each one of those would be. Now what you'll notice is the closer a coefficient is to -1 or +1, the stronger the correlation is. So we get strong correlations out near this end, out near -1, and we get strong correlations out here near +1. And the closer it is to 0, the weaker it is. So the closer we get to 0 right here, we can see that there's not as much correlation between the two of these. So what we want to do is we want to come back here and we want to talk about, we kind of want to classify, would this be strong or moderate or weak or perfect? So on this one, this is 0.64. So we're going to say that that's maybe strong or moderate. I'm going to write down moderate. Okay, so moderate on this one. Okay, because that's not a very big R value. That's not a very big correlation coefficient. And remember on this one, we found that this was 0.96. Okay, so I'm going to come up here and I'm going to write R equals 0.96. Now remember, it was negative. Okay, so a correlation coefficient that big, that close to -1, okay, this is very, very strong. In fact, we rarely see stuff like that that has that high a correlation coefficient. So that one's very strong. So we're going to slide back over here to the very end. And it says we've classified those as strong, moderate, or weak. We've got that taken care of. So do the self-assessment right here, but I do want to note this, and this is really important. That's why it's in red over here and it's bolded. Now, the classifications of strong, moderate, weak, and things like that, those depend on the data and the setting. There are times where a correlation coefficient of 0.5, whether it's positive or negative, that would be considered a pretty strong correlation coefficient, a pretty strong relationship. So that depends on the settings. These are really just guidelines that we've got right here. This is just to give you a rough idea. All right, good luck on the assignment.